Hey guys, Jared here with Kill Devil Diesel, and today we're going to talk all about camshafts. How big is too big? When do you need to put valve reliefs in your piston? How close can we run the valves to the pistons without getting into trouble? We're going to talk about a bunch of different specs on camshafts today. We're going to talk about lift and duration, which is kind of the figures everyone likes to compare. We're also going to talk about intake center line, overlap, intake and exhaust valve closing events. We're going to compare three different camshafts: the stock cam, KDD stage 2 camshaft, and a stage 2 sample that a customer sent us they'd bought elsewhere, and they weren't sure if they were going to need valve reliefs or not. And so we're going to take a deep dive with some of our camshaft measuring equipment here, and we're going to show you guys how to determine what goes into designing our cam profiles to be as drop-in as possible, and then some of the other options on the market and some things to consider when shopping around for a camshaft. Thanks for watching. Stay tuned. Hey guys, Jared here with Kill Devil Diesel, and today we have our camshaft measuring machine all fired up, and we have a couple of camshafts here that we're going to look at. The first camshaft is going to be the stock 6-liter cam. Then we're going to look at our stage 2 cam, and then and the reason we're going through all this is we had a customer who purchased a cam from somewhere else and wanted to send to us. I guess he had some questions on whether or not he was going to need valve reliefs with his cam or not, and and we're helping him with some other parts and working with him on pistons and other things. And so he sent us the camshaft sample to inspect, and we just kind of want to go over a few differences here on why some of this is really important. And so let's see, we're going to actually turn off the sample cams, and then we're going to turn off the KDD cam. And so right now here, if you can see my screen here, this is the exhaust lobe and this is the intake lobe. And so here is top dead center. Down here across the bottom we have degrees. This is crankshaft rotation in degrees. And then over here we have valve lift on this the vertical axis over here. And so basically what our cam machine does is has a rotary encoder, so it spins the crank and it measures how many degrees very accurately down to the umpteenth degree, and then it has a linear encoder that measures the the lobe lift. And then we can also turn on, so like here is the valve lift. This would be with the factory 1.4 ratio rocker arms. Now we are, we've got a few things we can talk about in a minute on rocker arms. We'll come back to that. But of course, with your stock cam, the cam obviously moves the lifter, moves the push rod, moves the rocker. Your rocker arm acts like a seesaw, and you have a rocker ratio. So, in the case of a 6-liter, for every 100 thousandths that it moves the push rod side up, it moves the valve side down 140 thousandths. And so that's called your rocker ratio. So there's a couple interesting things we're going to look at. We'll turn the valve lift back off. So this is just the cam profile. This is the factory 6-liter cam. And so we'll look at first, we'll look at our camshaft. So this is the KDD stage 2 camshaft. It's about 180 degrees at 50, meaning at 50 thousandths lift. The intake lobe has about 180 degrees of duration. And so we designed our cams to be as drop-in as possible. And so what does that mean? The factory cams on a factory virgin untouched engine, it's not uncommon to have piston to valve clearance issues on a factory 6-liter or 6.4 engine. And I think a lot of that's because they left the factory with a lot of piston protrusion, kind of relative to other diesels, and in the factory valve recession specs, kind of all over the place. So the factory Ford specs, the high side for piston protrusion is like 35 thousandths. And then your valve recession specs from Ford are like 13 to 27 thousandths on a 6.0 or 6.4. And That's important because you could be in spec technically at 13, 14, 15 thousandths of valve recession and be in spec at 34 or 35 thousandths piston protrusion, and you'll probably have piston to valve contact issues with a stock cam. And so of course putting in an aftermarket or performance cam is going to cause issues. So especially if the heads have been resurfaced a time or two or three, or if the block has been resurfaced, etc., then you might have to take extra precautionary measures. So for example, on our engines through Kill Devil Diesel, we run on all of our heads, whether you buy just the heads from us or one of our engines, we run the valves a little bit deeper in the heads. So the factory specs for 13 to 27 thousandths. We tend to be like 30 to 40 thousandths, and even on some of the race car stuff, we'll be even deeper than that. What that does is sinks the valves a little bit deeper into the head and get you a little bit more real estate in between the pistons and the valves. And we do that especially on the heads to make the heads really a drop in for, especially if people are, within the factory Ford spec. So we try to adjust that in the cylinder heads. On the blocks, we tend to be 20 to 25 thousandths piston protrusion, and it's really kind of on the low end of the factory specs. And we do that again to kind of minimize any possible chance of piston to valve contact. And so we highly recommend, if you do have the block decked, have your pistons decked too. Otherwise you're going to have, and you can actually buy the pistons with a 10 thousandth shorter, what they call the compression height. You can buy the pistons with a 10 thou shorter, right from Molle or UEM. And so a few options there. And so, why not just run valve reliefs? Well, valve reliefs are kind of a necessary evil to run a really big camshaft. And so there's no positives that come from adding valve reliefs other than you can run a bigger cam. If anything, the valve reliefs hurt performance. They knock compression out of the engine, so a lot of places, typically do like 100 thousandths deep valve relief. Well, by the time you delip the piston and valve relief it, you've knocked like 2 points or more of compression out of it. And sometimes, you end up down in that 14 and a half to 1, which is like what we run the blown alcohol engines on. So that's a pretty low compression ratio, especially for a street truck where we don't want our customers to end up with like a hazing issue, etc. So if we can avoid valve reliefs, we try to, unless it's going to be on 5,000 and 6,000 RPM sled pulling truck where there's enough benefit from the larger camshaft to really be worthwhile. And so, not all stage 1 cams are the same, not all stage 2 cams are the same. Stages really don't tell you a whole lot other than maybe kind of what the intended use was going to be for, and even then there's still a lot of variance from manufacturer to manufacturer. So our stage 2 cams were really designed to be a performance product where you've got upgraded turbo, upgraded injectors, maybe our Icon cylinder heads or an O-Dog intake that really helps with the airflow through the engine, and our cams work really well with that. And we designed them to be as drop-in as possible, again with kind of the caveat that some of the factory stuff can be all over the place. And so as long as you're within that 20 to 25 thousandths of piston protrusion and the 30 thousandths of valve recession, our cams will drop right in, no problem. And even if you're kind of within the factory specs, our cams are fine. They typically drop in and won't cause any piston to valve clearance issues. And so what causes piston to valve clearance issues? Typically, a lot of people think that this is the exhaust lobe and this is the intake lobe here. And so a lot of people think that piston to valve clearance occurs at peak valve lift, that putting in a cam with a bunch of lift is going to cause piston to valve contact, and that's really not true. So as we see here, this is TDC right here in the center. This is where the piston is at top dead center, meaning the very top of the bore, where the piston actually sticks out of the block, like we've been talking with piston protrusion. And so you can see here at peak lift, we're 90 to 120 degrees before top dead center on the exhaust, and on the intake we're 90 to 120 degrees after top dead center. So the piston's halfway down the bore by the time the valve is at peak lift. So they're nowhere near each other at peak lift. So typically your exhaust valve to piston clearance will be tightest at about 10 degrees before top dead center, and on the intake side you'll be about you're closest at about 10 degrees after top dead center on the intake. That's true for most engines, not every engine, but plus or minus a few degrees. Exhaust, you're typically closest about 10 degrees before top dead center, and that's where the valves are closing and the piston's coming up and chasing the valves closed, and right at that last few degrees right before top dead center is where they tend to be closest. And then kind of the opposite on the intake. The intake valves start to open as the piston's on it. They actually open before the piston's on its way down, as we'll see here in the graph, and they kind of chase the piston down. And so that's typically where you're closest. And so we designed our cams to be as safe as possible, so nobody has issues with piston to valve contact, et cetera, et cetera. And so knowing that, here in this, let's see, we can zoom in a little bit here to this overlap area. And so we see here 10 thousandths after top dead center. Let's see, let me move this out of the way. 10 degrees rather after TDC, the valve is opening 30 some thousandths. And so 35 thousandths. And so that's a little bit more than the stock cam. And you can see we keep the opening events pretty similar, nice good transition here. And nice good, one of our head engine builder, Kevin, said yesterday, if that was a plane, I would like to land on that plane. If that was the plane landing, that looks pretty good. More on that in a minute. And so anyway, this should be a good, safe, number. So you've got 30 thousandths of valve recession, 25 thousandths of piston protrusion, plus a 50 thousandths head gasket. And this gives you enough real estate in between the pistons and the valves. And same on the exhaust. You can see that, 10 degrees, before top dead center on the exhaust. This is our exhaust closing here. Here's the stock cam, and we are, we've added a little bit of lift to it, but we're still in a good, safe area here. So now we're going to turn on the sample cams that were sent to us, and these are in red. So the factory cam is in black and gray. Our cams, the KDD cam, is in blue, and then the sample cams that were sent to us, which is also a stage 2, is in red. And you can see that has about another 30 thousandths of valve lift on top of over our cam, and almost 60, almost 40 some thousandths more than the factory cam at 10 degrees after top dead center. And so for this customer, we told him, yeah, unfortunately, probably would want to run a valve relief with that camshaft. It doesn't have to be a full 100 thousandths deep valve relief, possibly 30 to 50 thousandths valve relief, which is, so he actually, we're going to mill up a set of pistons for him. So that way everything will drop in, and we won't have any, piston to valve clearance issues. And, we'll put a real small radius on the pistons to make sure that we don't end up in any kind of scenario where we knock too much compression out of it. And so anyway, it's kind of an interesting, deal here where if we assume that based on our measurements and the way that we build these engines, and, there's more than one way to do this, the purpose of this isn't to badmouth anybody else's camshaft. Obviously, we're not going to mention the company. It looks like a great cam. There's lots of good options out there. We're fortunate that, in today's world and today's market, we have lots of good options. And so this is a great option. It's just, unfortunately, puts the intake opening event a little bit closer to, piston to valve clearance than we would really like to be. And so for that reason, again, out of an abundance of caution, we highly would recommend this customer would run like a 30, 40, 50 thousandths valve relief to run if they're going to run that cam. But we noticed a couple other interesting things while we had it in here. And so, again, the purpose of this isn't to badmouth anybody's products, just to show you some differences on what's out there. So now we're going to turn off the lobe lift and turn on the valve lift. And so, again, through the rocker ratio, everything's kind of exaggerated. Whatever the cam lobe profile does, the rocker ratio is going to exaggerate that. And so now, one of the things that we want to look at is some interesting things that kind of pop out here is if you look at, let's see, we'll zoom back into, let's go over here to exhaust opening. And so if you look here, here's our cam. We start just a few degrees before the stock cam exhaust opening, which, by the way, is one of the most important figures when looking at camshafts. Lots of people compare lift and duration. Those are relatively easy numbers to wrap your head around. Exhaust opening, though, is actually intake center line and exhaust opening are kind of the two figures that I really tend to look at first. And that would be because the exhaust opening. So here's bottom dead center. This is the exhaust stroke here. The piston's on its way down. It gets to bottom dead center. And so this is what they call the blowdown area here. So this is the combustion stroke. I think I said exhaust stroke earlier. This is the combustion stroke. So the piston is still the explosion happened and it's driving the piston down. There's all this combustion pressure and it's driving the piston down. So it gets to bottom dead center here. And this is where it would start on the exhaust stroke over here. But if you can see, we actually open the exhaust valves, even the stock cam, way before bottom dead center. And so this area here is what they call the blowdown area. And that's where it's like shaking up a 2-liter bottle and cracking the cap open. that is going to, all that pent up pressure has to go somewhere. And so that's actually what we really want. And the earlier we can open that exhaust valve, drives more of that exhaust pressure and energy, again, like cracking open a 2-liter, that's been shaken up. And that big pulse of energy when the exhaust valves crack open is kind of really what helps drive the turbo a lot. And so, now if we open the exhaust valves too soon, we kind of start to take away some of that cylinder pressure from driving the piston down. So it's kind of a balancing act, and there's a lot of, RPM. It can be a big factor on where we're going to open the exhaust valve. But for, where most people drive the truck, 1,500 to 3,500 RPM, we've had really, really good luck here. But what we noticed is, so even the stock cam, has a halfway decent looking, ramp rate here. More on that in a minute. Our cam has a, maybe even a little bit better ramp rate here. The sample that was sent kind of doesn't really have a lot of a ramp rate to it. Again, in the airplane analogy, if this was the airplane that was landing, I'm not sure that I'd want to be on, the red line airplane. That probably wouldn't make for a really smooth landing or smooth takeoff. And so let's pan over here to the overlap area. So these are the exhaust valves closing. These are the intake valves opening. And so kind of the same deal. There's not really a lot of closing ramp here on this. So the valve, again, this is the valve, not the lobe. The valve is kind of pretty much going to, I don't want to say lawn dart, but, there's not really a whole lot of landing ramp here. Maybe it'll work fine. Maybe it's in an area where it just really won't kill parts, but it's a little bit concerning. And again, you can see the same on the intake opening too, and intake closing is kind of the same. So just kind of an interesting observation. You can see here, again, here's the stock, the gray line here, stock intake closing. Here's our blue line is our intake closing. You can see we hold on to as much duration as we can out here, but then we actually, we kind of hurry up and get the valve closed where we're actually closing the valve right around the same time the factory is. Same deal on the intake closing. We're closing the intake valve after after bottom dead center. So here's on the intake stroke, so piston's moving down, intake valves are open, we're letting air in, and the piston's moving down, drawing in that air charge. And again, this happens mind-bogglingly fast. At idle, that's like 4 times per second. At 4,000 RPM, it's like 40 times a second. Rough math on that. And so, the piston comes down and is, constantly trying to refill the cylinder, every 2 revolutions of the crankshaft. And so, anyway, if you hold that intake valve open too long, and the piston's on its way back up again, same deal, you start bleeding off more of that cylinder pressure going back out, past the valves again. And it also creates reversion and can do some goofy things for, during, especially on the intake, you can bleed off a lot of cylinder pressure by holding the intake open too long. Again, RPM is always a big factor on where we're going to open and close the valves at. And so anyway, kind of interesting there. But another thing that we can look at here, let's see, let me unzoom. And now we're going to look at what is called the velocity. And so this is basically, what is the speed of the lobe, the lifter, push rod, rocker, valve, etc. And so this kind of really tells the story of what we kind of see a little bit here on those kind of early opening ramp rates. And so if we look and zoom in over here, this is our cam, has a decent ramp rate, pretty gradual deal here. On this is exhaust opening, this is the factory exhaust, and you see the factory velocity has a much more abrupt start here. This one, cam has a very abrupt start. Again, I'm not saying that's going to cause a problem, but again, I wouldn't want to be on that airplane. So let's see, then we'll pan over here to our overlap area. Let's see, let me zoom back out. And so same deal, you can see on the closing, let's see, we can also pull up, we'll turn off velocity and we'll pull up acceleration. And this also kind of tells the same story. This is like the rate of acceleration of the lifter, the cam, etc. Again, and we've said before in other podcasts and stuff that there's kind of 2 main aspects of camshafts that are both important. One is lift, duration, intake centerline, overlap, etc. That whole group of camshafts kind of determines how the engine will perform, what makes the engine happy from an airflow performance standpoint. And then on the other hand is the ramp rates, the acceleration, the velocity, the jerk, and that all describes what's going to keep the cam and lifters and rockers happy so we're not breaking parts. And so, interestingly, let me turn off, it's kind of a lot to look at. Let me turn off the sample cams, and I'll even turn off our cams. And then if we look at the factory, valve lift here, you can kind of see this weird, this acceleration curve accelerates real hard, and then it kind of lays over and has this concave area here. And I think that's a big reason why 6 liters and 6.4s tend to tear up the lifters. If you look at for example, the 7.3 takes the same exact part number lifter as the 6.0 and 6.4 Powerstroke, and they very rarely kill the lifters. And I think there's a few reasons for that. I think part of that is probably the 6 liters have 2 valves and 2 springs, and all that per lifter, maybe a little bit more spring pressure. 6 liters turn a little bit higher RPM, but really it's the camshaft. And I think the factory 6 liter cam is just kind of a crudely mass-produced item that works. There's probably variants from cam to cam that we've seen too over the years, but if you look at the that kind of goofy abrupt and then concave acceleration curve is not really ideal. And so we'll turn that off. Again, we can pull up the actual lobe velocity as well. It's not as exaggerated. The acceleration curve, again, you can kind of see this is the lobe, not the valve. Same kind of goofy deal. So now we'll turn, we'll turn the KDD cam back on, and you can see ours has a little bit better overall curve to it. And we'll go ahead and turn on the sample as well. Again, kind of an abrupt opening, but it's at least a better curve than the stock curve. It's kind of a little bit more convex, which is kind of better. And so anyway, a couple interesting things here. Again, talking about the factory cams, why do they fail? We'll turn off the valve lift, and we'll turn on the lobe lift again. And let's go back in here and look at, we can turn on jerk, which is basically any time your lifter or push rod, etc., is going to change direction. And so there's a lot of different things that we can see zoomed in here that goes kind of beyond what the what the factory what just the lobe, what the cam card specs, lift and duration is going to tell you. And nothing here that stands out terribly. Here's really just we want to keep as smooth a line as possible. You can see the factory starts to jut up a little here. The red line's kind of all over the place. The factory, has some weird jerk movements here. Not terrible, but not awesome. And so again, I think some of that's why the factory cams tend to tear up the lifters. And so again, the main thing we wanted to kind of cover here was the valve lift question for our customer. And at the end of the day, I think this is probably a great cam for them to run. I think it'll probably perform great. Hopefully longevity is not an issue. But because of that earlier, and you can also see here how the red line is shifted. It's the whole curve is shifted a little bit earlier than our blue line. And you see that here in the intake center line. And so, for example, the stock cam is about 104-degree intake center line. On this other cam, it's a 98-degree intake center line. And so that's several degrees earlier, which is good. That probably helps promote low-end cylinder filling and all, which is really good as long as the pistons don't hit the valves. Anyway, it's kind of interesting. We took a little bit of a different approach. We wanted to keep the overlap about the same, because if you advance the cam, you get more overlap in this kind of area under here. And so it was a highly scientific here, but if you advance the intake lobe and keep the exhaust where it is, you end up with more overlap. Pros and cons of overlap: tends to favor high RPM, tends to favor very efficient turbo setups where boost and back pressure are equal. Now we're back to the engine's just an air pump again. And so anyway, too much overlap down low, especially with like a VGT or a S300 turbo where back pressure is usually higher. You actually get a little bit of like internal EGR. So we didn't want to increase the overlap. So we did want to increase duration. So we kept the intake opening side of the lobe, pretty close to factory, and we wanted to increase duration. And so the only way to do that is to move the center line without changing duration too much. And so anyway. Some interesting data, again, being able to tell 10 and 20 degrees before or after top dead center how much extra valve lift we're getting has been a really handy tool both in us prototyping and camshaft development. We're about to release our 7.3 Powerstroke cams that have been in development for a long time, and we've had 6.0, 6.4 cams for a long time. We've got a cool new, a few other cool new things in the works too. And so I'll show you here while we've got all this pulled up. We'll just use our stage 2 as example. We did a post the other day that got some questions on rocker ratio. So out of an abundance of caution, when we first released all the Jessel rockers for 6.0, 6.4, 6.7, and now 7.3 we released just last year. Out of an abundance of caution, to be conservative, we kept the factory rocker ratios. And so now that there's no issues, and we have heads that flow more at more and more valve lift, we can kind of come back and revisit with a really robust Jessel lifter, a bushing, there's no needle bearings, and a DLC coated body, etc. We can be really aggressive on the camshaft for a competition setting, and really aggressive on the camshaft, and with a higher rocker ratio, we get way more valve lift out of this deal. So let's see, we'll turn off lobe lift, we'll turn on valve lift, and then we'll actually go in here, and I'm going to change this to we'll turn on this other cam just for a visual. So you can see they're pretty close in lift and duration. We've talked about the intake center line changes. But what I'm going to do here is I'm going to go in and change the rocker ratio. So we won't change anything else. We'll just go in and change the rocker ratio to the new 1.75 rocker ratio that we have coming through Jessel shortly. And you can see the difference. We kept the duration the same, but just through changing the rocker ratio, we're able to get, almost an extra, 100 thousandths of valve lift. And so now that we have heads that flow at higher and higher valve lift, we can take advantage of that airflow, and the total, what they call the area under the curve, is actually much better. And so you can see here, if I expand this out a little bit here, the area is, you can see with that rocker change here, it really bumps the area up tremendously. And so anyway, some really interesting stuff here. We thought we'd do a video, a little bit of a different kind of a Tech Tuesday kind of a video for us here. But it's been a long time since we've really talked in depth about camshafts, and we wanted to do a video. So sorry it's a little bit long, but we wanted to do a video and kind of go through and explain exactly what all is going on here. And so anyway, if you have any questions on your build, if you need valve reliefs, what camshaft should you run for your application, or if you want to send us a cam, let me know. If you like this and want to see more deep dives, we've got some sled pull and camshaft development stuff we're working on, and we can compare. One of the other things we'd like to do a video on is comparing just how technology through the OEs has changed, 7.3 cam to a 6-liter cam to a 6.4 cam, 6.7 cam, etc. And so anyway, let us know what you'd like to see. We can do a breakdown of different cams and different engine packages. We can, dive deeper into the specs and what makes a cam live and survive longer, what tears up. I think we kind of covered what kills the factory 6.0 and 6.4 cams, and maybe how you can get into trouble, with ramp rates and stuff. So anyway, we wanted to kind of just do a deep dive. Again, we've got our, our camshaft forest back here. We've got a bunch of cams to test. More info coming soon, so let us know what you want to see in the comments, and we will chat soon. Thanks for watching. Thanks for watching. We hope you guys learned something. We take a lot of pride in engineering camshafts and load profiles that not only perform good but also last a very long time. We hope you guys learned something. If you have any questions, drop them in the comments. What do you want to see next? What do you want, what camshaft should we compare? What kind of data do you want to see? We have a lot of before and after testing, a lot of dyno testing lined up for later this year. So stay tuned. Let us know if you have any comments, and thanks for watching. Take care.